Okay, hello everyone. I know this is the second last talk of the day. Everybody must be already very tired. I'm going to talk about something slightly different. I'm going to dive into a little bit into the world of metabolomics, mass spec, machine learning, and static mass. So today I'm presenting the FraGNNet, a deep probabilistic modeling for mass spec predictions. The first is a quick outline of what I'm going to go through today. I'm going to define our research questions and introduce our method, show some results, and quick question sections. So here is a very typical MS working flow where the input is the biosamples, biosamples people are interested in. In the wet lab, the technician going to collecting high resolution MS spectra out of your biosamples. And through the very sophisticated column, we can assume each mass spectrum collected in this set will be corresponding to only one single sample. And to identify the molecular structure of interest through the mass spec, we usually do a matching and ranking against a spectral database, and where the bottleneck of this whole working flow exists here is the size of the spectral library you can have. And the standard libraries at right now is the NIST mass spec library, have around 40,000 compounds being ever in there. And the size of the most common used compound library, PubChem, have around 120 millions, which is about like 2,000 times to 3,000 times larger than that. And someone estimated the entire chemical space have 10 to the power of 50 molecules in there, which is enormous. Then compared to the little size have on 37,000, and the gap is obvious. So therefore, in the last couple of decades, there is a lot of effort to use in silico methods to try to fill the gap. With the same working flow, instead of only rely on the experimental collective spectra, we take the input of the compound database and send it into a spectral prediction models. Then we can build a in silico spectral database to fill the gap of the lacking of the reference mass spec data. Just keeping in mind, the compound database in here does not necessarily have to be the real compound database. This can be simply replaced by any machine learning model to generating never be seen before structures. So here we are introducing our goal of the our latest approach to tackle this problem. We call it FraGNNet. It's a combination of recursive fragmentation generations coupled with deep learning methods. We have applied machine learning methods to both input structures and fragmented graph. The fragmented graph itself representing all possible fragmentation pathways from the precursor structure to its fragments. We're also mapping the fragment to formulas, then produce the high-res MS spectra, and also introduce the peak structure annotations for every single predictions. So here's a quick overview of the 3 steps we're doing. For every single input molecule, the first step, we're going to generating the fragmentation graph, and we're also going to have a molecular embedding. On the second step, we're going to infer fragmentation distributions, which is a probability of each fragment going to present in the final mass spectra. At the final step, we're going to convert the fragment distribution into a in silico spectra. I know it's a mouthful, so we're going to go to this in depth a little bit. So here is the first step when we're getting the precursor structures. The first step is to creating this fragmentation graph, where fragmentation graph essentially is a DAG, a directional acyclic graph. In our design, each node only representing a fragment from the original molecules with a certain amount of hydrogen tolerance. This is designed to take into account of a hydrogen transfer occurred in the fragmentation process. Each edge on this graph is a simplified fragmentation pathways. It's just indicating it is possible with bond cleavage from your parent ions translated to the child ions. Once we have the fragmentation, structure itself, it's very easy to just calculate all the possible formulas per each node. As the example I showed here, we highlighted in gray. These substructures have 2 carbons and 1 oxygen from the original structure, with a tolerance of plus minus 2 hydrogens. It can cover a range of formula from 2 carbons, 1 oxygens, and have up to have a range of 2 hydrogens or 6 hydrogens. While the mass spec ultimately rely on the molecular mass of each formula, from each node, it's very trivial to deducting all possible formulas can be produced. All possible molecular mass can be produced from this node. Well, as the example I show here, I use the same constraint. The same node is essentially possible to result in the molecular mass ranging from 42 all the way to 46 daltons. Yes, with the fragmentation graph generated, we can start to think about how to mapping the fragmentation graph into the final spectrum using probabilities. The first definition I want to introduce here is called node distributions, P of node. That's essentially is a probabilities of how likely this particular fragment is going to be occurred in the final spectra. For instance, we showed the number 1 and number 3 are representing different heavy atom skeletons with their allowed hydrogens. The color here indicated the more likely. Well, in this example, the color here indicated the downstream ones are more likely occurs. And the second definition we're going to do is called the node formula distribution. As I just showed a couple slides ago, every single node have multiple formulas attached to it. And therefore, a node formula distributions showing given a particular node, what's the probabilities we're going to show this particular formulas occurs on our spectra. To calculate the total formula distribution, P of F, that's essentially just a summations over multiplications. Just keep in mind, different node in a fragmentation graph can result in the same formulas. As the example shows, the formula 3 is possible being produced by the node 1 or node 3. The last one in this little journey of all the probability distributions is to try to calculating the mass distributions. We know that each formula have a unique molecular mass. Therefore, the particular the total the probability of a mass is also a summation of the products. To take into account where the experimental data have and the theoretical molecular mass can result in a small difference we call mass range, we modeled the particular formula distribution using a narrow Gaussian. In this case, the standard deviation choose is 10 ppm based on the molecular mass of the formula. I just introduced all those probability terms. How we're going to put them all together, right? So essentially we are modeling mass spectra as a distribution over molecular mass, a P of M. The P of M can be deducted from a summation over the products of the node distribution, the formula distributions, and the mass distributions. Then the formula distribution can be substituted based on the equation in the red, the blue and red. By modeling the mass spectrum in this way, the entire distribution is conditioned on the original molecule structure only, and the parameters can be learned from neural nets. Another nice thing about this probabilistic formulation is that we can simply just optimize a negative log likelihood based on our probabilistic formulations. So here is another overview. We saw a slightly different version of this graph a couple slides ago. Here we introduced 2 neural nets on each stage. The first graph neural net is going to used to learning the molecular structures, where the second graph we're using the embedding from the first graph neural nets, and the fragmentation graph try to learning the fragmentation distributions. And finally, we'll be able to mapping what we have learned into a in silico spectra. Does it work? Well, here's our training and evaluation set. We are taking the NIST-20 data set. We merge all the spectra based on their structure and Alex type. In total, there are about 13,000 merged spectra for training, 4,000 merged spectra for evaluations. Our model size are relatively modest. It only have 1.7 million parameters compared to the latest models in this field, which is a mass former, have somewhere up to 20 million parameters. Training on our merged spectrum in this case can be done on a single A40 GPU, take around 12 hours or less. Here is a little bit. Here is a plot. Here is our performance on the testing split. We have compared our models with three other state-of-the-art approach before. The Asperger from the MIT, the mass former also from the U of T, and a NIMS it was a Google models. Just keep when we compare in the compare using the cosine similarities, which is a popular metrics when we measure the spectral similarities. We provided two set of performance here. In the green, we use 10 ppm as the mass matching threshold. In this case, only FraGNNet and Iceberg was able to produce performance, where the FraGNNet have a substantial lead over the Iceberg. We also evaluated the BiC spectra on the using cosine similarities. The BiC size is 0.01 Dalton. Our method still have holding a lead against rest of the field. But this is only done on a so-called inch key split, where a much harder ones can be tested on the special way to split data called scaffold split. This is used to simulating a discovery, simulated the workflow to think haven't been discovered molecules. In this case, all models saw a performance drop, but ours still have a lead over others. Okay, but this all starts, and you guys all want to see an example. Now, here's a pretty pictures everyone want to say. On top is a real spectrums, and the bottom is our predictions. As I said before, we are able to provide annotation for every single peak. Therefore, on the very right here is the highlighting the structures of our model predictions. Two interesting points I want to point out is the first, the fragmentation 1 and fragmentation 2s are essentially the same substructures but have a different hierarchy configurations. And in the row in the number 4, our model is actually able to learn all those three things. Essentially, is the same underlying structures, but coming from different atom set. Well, the last testing it is because what I want to show is because we said we want to the idea of this is to facilitating better structure retrievals. Here we tested two state-of-the-art performance predictors on PubChem, and there is like 4,000 in 4,000 the retrieval cases. Our model is able to do about a 25% top 1 and 82% at top 3, which still surpassing our competitors. So in conclusion, the FraGNNet is a novel method for mass spec predictions with pretty simple with probabilistic modeling. It has state-of-the-art performance on spec predictions and the compound retrieval tasks. It's meet the key requirement in the area of the resolution, scalabilities, and interpretabilities. And special thanks to all the collaborations and support from 2 different universities and AMI and Vector Institute. And if here's the QR code for our preprint, and feel free to send us emails.
Thank you, Fei. We have 2 minutes for questions, so if anybody has a question, please come to the microphone.
Hello, thanks for the great talk. Can you maybe comment on prediction throughput of FraGNNet, both on CPUs and GPUs, such as the A40?
We can do about, at the moment, we can do a couple million predictions per day. It's definitely slower than just using Massformer, because we have to generating the Framington graph first.
Yeah, I can imagine that the graph is quite computationally intense to generate.
We actually can manage to generating the Framington graph under roughly under 1 minute per molecule.
All right, thank you very much.